What's up, everybody? Today we're going to now look at the matlab example to prove the time delay system's stability, right? And first we are going to use time delay independent stability, LMI stability criterion, and that was that criterion, right? And by the way, before anything else, and I constructed some document, right? You can, together with the code that I'm going to show you, and you can download that from the GitHub link using the GitHub link down in the description. Okay, all right, this is the first we are going to look at two examples, and this is example one. This is from Duan and Yu Atomizing Control Systems book, right? And this is the example. Here we can see A matrix, and we can see the weighted AD matrix. Okay, and these are input and disturbance signals. However, we are not going to be worrying ourselves about those, right? Okay, so consider those U and W disturbance signals non-existent. Okay, so okay, this is A and this is AD. So the problem is this, and this is the independent condition, right? So the problem is this: find P and S such that those given conditions hold. Okay, again, A and AD, right? These are the things that we know, and P here's, and this is P, and S minus S and S, P being positive and that Block matrix being negative definite is two conditions that we need to satisfy, right? YOLMIP is the toolbox that we are going to use, LMI toolbox, right? Okay, now let us look at the problem, right? So I called this F001, right? You can download the MATLAB codes as well using the GitHub link down in the description section below. Okay, so right, this is like clear, right? And by the way, STP-T3, not only you need YOLMIP, but also you need to have some type of STP solver, right? And STP-T3, right, is the solver that I use. Of course, you can use like Mosaic or something, right? There are other solvers as well. Okay, so these are kind of, you can consider that like in C++ and adding the library or importing the library, right? This is something like that, and I hope I can get that done, the video about how to install YOLMIP and STP-T3, right? The new versions, hopefully in the future, I guess. And okay, so I added the libraries, and all right, so this is the first code. Here I define A and AD matrix, and this is the state dimension. Okay, and this is epsilon. We talk about this all the time, right, in the previous videos as well. And this is kind of required for numerical accuracy. For example, you cannot say A greater than 0. You cannot put that type of constraint, right? You can put inequality. However, we really need this matrix to be positive, definite, right? In that situation, you will do something like that: epsilon times identity, let's say the dimension of A, 3, for example, right? So this is the logic. Okay, so epsilon is something like that. All right, P and S are the decision variables. I just, of course, you would like them to be, I mean, this is the thing that you will use, right? But I just to put some additional constraint. For example, these two lines, I mean, this is optional. Okay, the correct one is these two lines. Of course, they need to be symmetric, and being diagonal is like an addition of unnecessary constraint, right? I'll just put that those constraints just to see if that's possible to obtain diagonal P and S matrices, right? Okay, so P and S, they don't have to be diagonal, is what I'm saying. Okay, all right, and this is F. Like in the previous videos, we put our constraints, right? What was our constraint? See that P being positive is the first constraint, and this block matrix being negative definite is another constraint. And now I can hear you say, but you didn't put epsilon, right? The reason is that in the Doğan and Use book, it says that system is asymptotically stable. However, although I don't like to say they kind of make a mistake or made a mistake or something, however, this system is stable in the sense of Lyapunov. It is not asymptotically stable. The first state, now we're going to look at the simulations as well, right? And it doesn't converge to origin. Okay, so I first try this. I first try that, and this is like the correct one you will do. But then I couldn't find P and S matrices. It's always given me like infeasible problem, infeasible or numerical problem or something, right? And that's when I realize maybe I should, you know, take a step back and ease the constraints a little bit, right? If there's something additional wrong is going on, I wanted to investigate that. And this constraint in that form, this line and this line, for example, this line indicates that V, the Lyapunov function, being positive definite. Okay, this is like strictly positive definite. Okay, not semi-definite. Positive semi-definite. It is strictly positive definite. Okay. However, this being negative semi-definite indicates that V dot is negative semi-definite, right? So in that situation, we only proved, if we did that, we only proved, well, how should I say, stability in the sense of Lyapunov, not asymptotical stability. Okay, so, and these two constraints are like just to, you know, put additional constraints. You don't need to do that. Okay. However, you would like to pull some constraints. Otherwise, not for this problem. This is relatively small scale. I mean, this is really literally the small scale problem. However, for other, you know, larger dimensional problem, you would like to, because we have, since we have like lots of degrees of freedom, right? We would like to put some constraints. Okay. So this is just this line is stating that, hey, I am going to use STP-T3 STP solver, right? I am stating that to YOLMIP, okay? And since there is no objective function, this is only a feasibility problem, right? Here, this is option, right? And F is contains our constraints, okay? And solution.info, you can look at that if that is like feasible or some kind of numerical solutions have happened, right? You like to look at that. And after that, you get the P and S variables, and you can look at the eigenvalues to see if they are very positive definite. And you can also look at the eigenvalues of that, you know, block matrix to see if that's very negative semi-definite or negative definite. Okay. Okay, so let's run that. Okay. First of all, it says successfully solved, and also termination code STP-T3 0 indicates that, yeah, problem is solved and no problem occurred, right? And this is P matrix, right? 1, 2, 3, okay. 22, 42, okay. And so this is P0, and this is S0, and the eigenvalues of the P matrix is like positive, and eigenvalues of S matrix is positive again, and we want it to be, by the way. And let's look at the maximum eigenvalue. And since this is negative, however, it is like the numerical precision, right? Almost. So it is actually not that negative definite. It is negative semi-definite, right? So we only proved in that case. And now we are going to look at the simulations. We only proved Stability in the sense of weapon of. Okay. So let's look at the. Yeah, this code is important actually. Yeah, now that I realize that, I need to also talk about this code. Okay. So I am going to also put another link in the description, and that link, using that link, you can watch a YouTube video about this code. I seen somebody explaining DDE23 code, right? MATLAB, and code that is used for delay ARTI also. You can use that for nonlinear. However, this is DDE. DDE stands for delay differential equation, right? And DDE23 is the ODE 45, or I should say that, one second. DD24 is the time delay version, TDS, time delay system version of OD45. Okay, so you cannot use OD45 because it is not a ordinary differential equation. It is delay differential equation. It's like another type, right? It is almost like, for example, OD45. What is the primary function of OD45? OD45 primary function is initial value problem, right? However, there is also another problem type called boundary value problem, right? And for that boundary value problems as well, and hopefully in the future we'll look at that, you cannot use OD45. You need to use, what was that? BV. Let me write that. This is totally unrelated, by the way, but let me write that. BVP or C, right? And there's also BVP 5C and BVP init. Okay, this is for boundary value problems, BVPs. Okay, and for ODEs, we all know OD45. Okay, and also DDEs, right? The delayed differential equations, right? We have DDE23, also DDE ST, state dependent delay differential equation, right? Also DDE and ST. This is like really interesting type of systems. So in that, I mean, these are complicated. I shouldn't be talking about them. Okay, in this video at least. Okay, so now what we are going to do. Okay, let me explain DDE23. Okay, first we only have one delay, right? We only have one delay. Okay, let me show you what I mean when I say one delay. Yes, I consider that d of t is a constant number, 0.1 seconds, for example, right? We only have one delay. Okay, however, there can be cases where you have x1 of t minus 0.1 and x2 of t minus 0.3, right? In that case, we have two types of delays, 0.1 and 0.3 seconds, right? Okay, so those delays, you need to put them in a vector, right? And then you will let MATLAB to know about them. Okay, so now that I talk about this, I feel like I should make a video about that. Okay, all right, let's see. So we only have one delay and it is 0.2 seconds. Okay, and like in the OD45, we have a time vector, right? T span, it's called, right? 0, and this is the discretization. You don't need to put that, right? But I wanted to put that explicitly. Okay, and this is like figure, right? So I did it just to make, doing the same simulation where the initial points starts from different locations in state space, right? Okay, so dd23, this is the form that you would use. Okay, it says solution 1. Okay, so 1 2 3 4, it takes 4 arguments, right? So first argument is the give me your differential equation. Okay, or rather DDE equation. Okay, delayed differential equation. Okay, I define that here. So we have t x. Usually if we were using OD45, we would only use t and x as parameters. However, in addition to that, we also have x rate, right? And take the x values, just allocate some memory, and also, you know, get the x1 delayed, and since this is like two-dimensional, x1 delayed and x2 delayed. Okay, and A and AD matrices, we define that also here as well. Okay, so, and this is the, okay, let's compare that maybe. Okay, come on, maybe compare that. Okay, here x dot here, and A times x here, A times x, and AD matrix times x delay is, we called x delay, right? Okay, and we just ignore un disturbance w matrix. Okay, so all right. In addition to that, let me show you. Okay, we explained first argument and lags, like lag times, right? Okay, or delay, rather delay times 0.2 seconds. We only have one delay time. Okay, so, and this is the x history. Okay, and this is, okay, let me show you here in that location, here in that. Okay, so this is TDS, time delay system, right? So usually we have initial values, right? However, for that type of cases, for that type of systems, our initial value is not like a point in state space. Our initial value, quote unquote, our initial value is a trajectory, right? Let's say t here is 3, right? Let's say 3. So our initial condition is a signal, right? Comes from or takes values between -3 and 0, right? Let's consider t max is 3, right? -3 and 0. Okay, phi, our initial value, not initial value, our initial trajectory of our states. Okay, so that's why we also need to state our, or indicate, provide our initial trajectories of our system states. Okay, so that's the difference between OD45, and yeah, that one and that one makes the difference between OD45. Okay, so after using that, right, we use deval auxiliary function to retrieve our x or state signals. Okay, and like x1 trajectory and x2 trajectory, or x1 signal and x2 signals, right? Okay, and we are just plotting them, right? So we explained that, and now let us, I forgot about talking that. So this is our trajectory, right? For example, 0.2 seconds, right? So basically here we are indicating, and since we are just given one value, right, it's like constant signal. Okay, x between -0.2 seconds and 0, right? 0, right, initial time, and takes a constant value. Okay, continuous, right, constant value. Okay, so what I'm trying to say is that you can, maybe I should do that actually. You can do something like this. Sine t and sine 2 times 3, right? You can do that. I will try to do that, by the way, right? And that indicates in that duration, right? 0 is our initial time. Okay. However, we have 0.2 seconds delay, so we need to take trajectories between minus 0.2 seconds and 0, right? Okay, because we are going to use those, portion of the signal, right? Because it is a delayed differential equation here, right? What would you do? Let's say t equals 0, okay, and d equals 0.2, okay. 0 minus 0.2 equals minus 0.2. Well, what is minus 0.2, right? Exactly, we are indicating that. That's why we need to have the trajectory of the states between minus d max and 0, right? Where the whole system operates, okay, starts to operate. All right, so let's run that code, right? Control enter. Okay, right. Okay, x1 here, maybe I should make it bigger. Okay, x1 red and x2 blue. x2 converges to 0. However, x1 doesn't, right? And however, x1, it's not like x1 is unstable, right? The system is not unstable. However, it is not asymptotically stable. It only is stable in the sense of Lyapunov. Okay, I wanted to explain that. Right, maybe let's do that. By the way, let's like 5 times. Okay, this is, yeah. Okay, this is it. Again, blue, x2 state converges to 0, x1 doesn't, right? And okay. And one more thing about that example. Let's make something like this, and let's something like this. So to see phase plane, right? Here we can see that x1 and x2, right? And x2 converges to 0. However, x1 doesn't, right? So all the points converges to that line. Okay. And where is that, by the way? Okay. Here's that. And all of those, okay, this is the PDF document that you can use. You can download from the GitHub link down below. And what I'm explaining here, I just documented, right? I just documented and everything what I'm explaining here. Okay, and now we are going to take a look at the example 2. Okay,